Alright, let's dive into something mind-bending today. Have you ever stopped to think about how a beam of light can cross the entire universe in what feels like no time at all? I mean, it's a photon traveling a billion light years, and yet, from its perspective, no time has passed. Personally, I think this is one of the most fascinating consequences of special relativity. What makes this really interesting is that it challenges our intuition about time. We're used to thinking of time as this universal clock ticking away for everyone, but in reality, it's far more complex. Time is relative, and it depends on your speed, your location, and the path you take through space-time. Here's where it gets wild. If you take a step back and think about it, this means that time isn't a fixed backdrop for the universe. It's more like a fluid, shaped by motion and gravity. For example, imagine two identical atomic clocks. You sync them, then send one on a high-speed journey while the other stays put. When they reunite, the traveling clock will show less time has passed. This isn't just a thought experiment, it's been proven. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world and compared them to stationary ones. The results? Exactly what Einstein's theory of relativity predicted. Now, let's talk about light. What many people don't realize is that light doesn't follow the same rules as other objects. If you throw a ball from a moving car, its speed adds to the car's speed. But light? Nope. Whether you're standing still or zooming through space, light always travels at about 299,792 kilometers per second. This is why Einstein made the speed of light a cornerstone of special relativity. It forces us to rethink how we measure distance and time. If everyone measures the same speed of light, then observers in motion relative to each other can agree on both distance and time simultaneously. Hermann Minkowski took this even further in 1908 when he introduced the concept of spacetime, a four-dimensional fabric where space and time are intertwined. From my perspective, this is where things get truly mind-blowing. Faster motion through space means slower passage through time. It's like the universe is balancing the books, ensuring that the speed of light remains constant. Now let's visualize this with a light clock, a simple device with two mirrors and a pulse of light bouncing between them. When the clock is at rest, the light travels straight up and down. But if the clock is moving horizontally, the light takes a diagonal path because the mirrors are sliding sideways. That diagonal path is longer, which means the light takes more time to complete each trip. Since the speed of light can't change, the moving clock ticks more slowly. This is time dilation in action. What this really suggests is that time isn't just a linear progression, it's a geometric property of space-time. And here's where photons come in. Photons are massless particles that always travel at the speed of light. Because of this, their proper time, the time experienced along their path, is zero. A photon crossing a billion light years doesn't age, doesn't tick, doesn't experience time. It's like the universe is saying, you're moving so fast, you're not allowed to experience time. One thing that immediately stands out is how this connects to the limits of cause and effect. Light marks the boundary of what's possible. Nothing with mass can reach the speed of light, and no signal can travel faster. Along that boundary, time doesn't just slow down, it stops. This raises a deeper question. If time can stop for photons, what does that mean for our understanding of reality? Even curved spacetime, as described by general relativity, doesn't change this. Light passing near massive objects like stars follows a curved path, but its proper time remains zero. This isn't just theoretical, it's practical. GPS satellites, for example, rely on these principles. Their clocks run slightly faster due to weaker gravity, but slower due to their speed. Without accounting for these effects, GPS would be useless within hours. If you take a step back and think about it, this all points to a profound truth. There is no universal clock ticking behind the universe. Each object experiences time differently, shaped by its motion and the gravity around it. Light, in a way, is the ultimate traveler, crossing vast distances without aging, without experiencing time. So, here's my closing thought. What does this say about our place in the universe? If time is so relative, so dependent on motion and gravity, are we truly experiencing the same reality as everything else? It's a question that keeps me up at night, and I'd love to hear your thoughts in the comments. Let's keep the conversation going because, honestly, this is the kind of stuff that makes physics so endlessly fascinating.